Welcome, warm welcome. Thanks for being here. Get yourself ready with a notebook, a pencil or a pen. Anything you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. Today we got a problem from the 2001 AP Calculus exam. It's the BC exam, but I think this question is most likely very approachable by someone in Calc AB. So if you're in AB, don't be scared. Go ahead and pause the video, give yourself a moment to work through this. These points here are 2, 15, 18, 15, 10, negative 15, and 14, negative 15, in case it wasn't clear what those values are. All right, when you're ready, you can join back and watch this walkthrough. Let's get started. We have a car traveling on a straight road with velocity 55 feet per second at time t equals 0. So that is an initial condition that's given. The graph here is the acceleration, so it's the derivative. Basically, we're looking at the graph of the derivative, and we're given an initial condition about the original function, which is the velocity. The domain here goes from 0 to 18 seconds. The car's acceleration is the piecewise linear function. So all of these are straight line segments. We have a little segment, then it goes down, then a flat segment again, and then it goes up. Okay. The question is, part A, the question is the velocity of the car increasing at t equals 2 seconds? Well, if the velocity is increasing, that means the derivative is positive, which basically means I was going to put a of t or a of 2. A of t is positive. So we're just asking if the graph is positive at t equals 2. I mean, it's pretty obviously positive. Remember, this graph's value is the slope of the velocity. So even though this is a flat line segment, it's a positive value, which means it's representing the positive value of the slope of the velocity, which means the velocity is increasing. So we say yes, and our reason why is because a of t is greater than 0. In fact, now I can be specific, and now I can say because a of 2 is greater than 0. Specifically, that's why. Okay, very easy. Part B, at what time in the interval other than t equals 0 is the velocity of the car 55 feet per second? So at what time other than t equals 0, obviously, that's where it starts off at 55 feet per second. Well, what you have to understand is that the velocity is increasing according to the integral of this graph. So that is adding velocity. So by the time we get to 6 seconds, we have added velocity. Okay, but that means that as we pass 6 seconds, now we're decreasing the velocity, and we just need to decrease it back to where it started. So there could be more than one time where it hits 55 feet per second, but when that happens, we would say that the integral up to that point is 0, meaning that the overall change in the velocity is 0, therefore it's at 55 feet per second. So I've cut this up into what seems like nice equal parts. Let's just make sure that's true. So from 0 to 6, we have this trapezoid that has a height of 15, and this base up here has a width of 2, a length of 2. Well, that's the same thing we have here. We have a trapezoid that goes downwards by 15, and then this little segment, if I make sure that that is a length of 2, then they'll have the exact same area. So what I can say is I can say that the integral, maybe I'll write it out here, the integral from 0 to 12 of a of t dt is equal to the change in the velocity over that time, which means v of 12 minus v of 0. So therefore, v of 0 plus the integral from 0 to 12 of the acceleration, which basically means the starting velocity at 0 plus the change in the velocity from 0 to 12 is going to result in the velocity at 12. Kind of makes perfect sense there. Okay. Yeah, so we know that this is equal to 0. We don't really have to calculate it necessarily, but we could. We can say that it's the integral from 0 to 6 dt plus the integral from 6 to 12 of the acceleration. And that is simply going to give us like 0, because this will be 1/2 base 1 plus base 2 times the height, 15, and then this would be 1/2 base 1 plus base 2, but now like the height of the function is negative 15, so those clearly cancel each other out. Is there another time when that happens? I don't believe so, because here we're going to get some more negative area in a trapezoid, and then we're just going to have this triangular portion, which I believe cancels out with this, but it doesn't cancel out the entire trapezoid, so it seems like we're always going to be under 55 after that. So we'll say at t equals 12. And it's because the integral from 0 to 12 of the acceleration is 0. Okay, not too bad. Part C. On the time interval from 0 to 18, what is the car's absolute maximum velocity, and when does it occur? Well, we kind of worked through a little bit of this, but let's look through it again, left to right. This graph tells us the change in the velocity. Anytime we have a positive, we are kind of like adding to the velocity. And then at some point, we stop adding to it and we start subtracting quite a lot. So the maximum is going to be at this spot here. Now, what is the maximum velocity? That we have to find by using the integral, because it asks what is the maximum velocity and what time does it occur. So we know that this is going to be a maximum of the velocity because max of v, because its derivative, which is the acceleration, goes positive to negative. Now, technically, when we're looking for absolute maximums, when they say that, they want us to check the whole interval. So we know that at first, v of 0, is 55. V of 6 is going to be 55 plus the integral from 0 to 6, which we actually calculated by looking at those trapezoids earlier, so that's not too bad. It's going to be 55 plus 1/2 base 1 plus base 2, which is 8, times 15. 1/2 of 8 is 4, so 4 times 15 is 60. And that's going to give us 115 feet per second. I don't know what that is in miles per hour. It doesn't really matter right now. So that's the highest so far. This is definitely not the highest. We know that at V12, it's going to be basically back at 55. And then it's going to continue to subtract all the way until 16. We're going to basically subtract another, it looks like an equivalent trapezoid. It's not quite an equivalent trapezoid. It has a slightly different base. But we can say that V16 is less than V12 because the integral from 12 to 16 is negative. And as we looked at, we don't really have to check it, but at the end of this, at 18, we have added some of the velocity back, but we do not get to 55. So I guess it's enough to just say that V of 18 is less than 55, and that's because V of 18 is equal to V of 12, which is 0, plus the integral from 12 to 16, that's going to be the negative portion that we continue subtracting, and then plus the integral from 16 to 18, which is a positive portion, but it's not more. What I'm saying is that I should say minus x and then plus y. Basically, this integral subtracts more than this adds, so therefore this has to be less than 55. Okay. All right. Last one, part D. At what times in the interval, if any, is the car's velocity equal to 0? Interesting. When is the velocity equal to 0? Well, We know that it gets larger up until 6, and we know that it goes back to 55 by the time we get to 12. Let's see if we subtract enough velocity from 12 to 16. 16 would be the only possible location where it should have passed 0. That's the lowest value. What I'm saying is that 16 is the lowest value of the velocity. So if it's going to have reached 0, then it's going to reach it by then. If not, then it will never equal 0. So we know that v is a minimum. We haven't calculated what the minimum is yet, but we know that it has a minimum at t equals 16. So let's take v12 and let's add the integral from 12 to 16, which we keep kind of referencing. It's some negative value. Now let's actually find out what it is, and that's going to be equal to v16. And if this is not less than 0 or 0, then it's never going to reach 0. So we have 55, that's v12, plus this integral from 12 to 16. Well, that's going to be the area of a trapezoid. We have base 1 plus base 2, which is 4 plus 2 now. All right, we can go back to the graph to look at that. But from 12 to 14 is 2. From 12 to 16 is 4. And the height of the function, which is kind of like the height of the trapezoid, is negative 15. So we're going to have half of 6, which is 3. It does get pretty close. It gets pretty close to 0, but not quite 0. We have 55 minus 45. So the lowest speed, or lowest velocity that it has, is 10 feet per second. That's the minimum value. So we can say that it never reaches 0. I'll be even more specific. V of t never reaches 0 on that interval. Okay, and our justification is because even when it reaches its minimum value, it doesn't hit 0. So that's pretty self-explanatory. If that's the lowest it goes, then it doesn't hit 0. All right, so that was a velocity problem where you have to understand that they're giving you the acceleration and asking about the velocity. So that means they're just giving you the derivative and asking about the original function. It's no different than being given f prime and we're asked about f, which is the antiderivative or the integral. All right, so really, it doesn't matter that this is a velocity and acceleration. They didn't ask any particular motion questions like the speed or something like that. They were really just asking about minimums, maximums, and if it ever equals 0. So you should be pretty comfortable with that, using the Fundamental Theorem of Calculus basically the whole way, because questions about the velocity are really asking us questions about the integral of this function, along with this initial condition. Don't forget the initial condition. It's very important. All right, that's enough blab out of me. Hope you learned something here. See you next time in the void.